And now to today's presentation. We are pleased to introduce Dr. Song Xu. Dr. Xu is a senior application scientist with Agilent's Nanotechnology Measurement Group, located in Ann Arbor, Michigan. His current responsibilities include applying existing technology to solve real-world research problems and demonstrations of latest technology in collaboration with AFM scientists. We are ready to begin. It gives me great pleasure to welcome Dr. Xu.
Good morning, everyone. Thank you for spending time with me. Well, today's topic, it's going to be the analyze your sample and project, choose the right tip and parameters. We have done this kind of e-seminar for the last several years, and it's always need to put together presentations and discussing about theories and practices about the choose the tip and parameters. However, people still find it they are facing lots of problems. For example, the biggest problem that people are saying is that they're facing way too much choice. Because as you can see, when you go to shop for AFM cantilever tip, the parameters are just all over the place. Spring constant vary from 0.01 all the way to 100. It's like, 10,000 times difference. The sharpness also 2 nanometer all the way to 50 nanometers. And people always ask, should I use sharp tips, or what's the point even have non-sharp tips? And there's also combined with different coatings, different imaging mode tips, and scan parameters, force parameters. It's just too much choice. So today's presentation, the first part of it, I'm going to quickly go over some of the things we already gone over, and then I'm going to rush the first 20 slides very quick because these has already been covered by previous web seminars, e-seminars, and I can always, we're going to put the PDF file there. You can always read by yourself, and you don't need me to read line by line. So let's quickly go over about those choices, parameters, imaging modes, and tips. And then after that, the second part of the presentation will give you just a lot of case studies, case by case, and what tip do I use and what parameter do I use. So it's much easier for you to compare your sample to the closest sample that I presented, and then try to maybe take consideration of my suggestions. All right, some go over review of the imaging modes. We have two major imaging modes, contact mode and AC mode. Contact mode, it's very simple to operate, and you can imaging contact mode in air and in liquid. These two imaging media are extremely different. In air, the force is always very high because capillary force. In liquid, you can actually bring it to very low force. And one of the biggest advantages of the contact mode is actually you can use the tip to clean your sample. Now, these are I will say, the advanced derivative imaging mode based on contact mode. For example, current sensing AFM, also known as conductive AFM, force modulations, scanning microwave, frictional force imaging. These are all contact mode imaging modes. Okay, now let me quickly go to the next slide. Here's an example of contact mode and what sort of resolution you can get when you have the right parameters in imaging media. I'm going to go into detail on this particular sample in the case study. When you use the right correct imaging parameters and tips, you can get a very high resolution. As you can see, this little itch pits, it's only 0.23 nanometer deep, and maybe 10 nanometers across, actually 5 nanometers, 10 to 20 nanometers across. So very good resolution. Now, the problem of the contact mode is, of course, the tip can itch a soft sample. For example, when you image something like a polymer, as you scan forward, you can actually see the surface actually changes. That's because you're actually scratching your tip. Now, some people use that scratch to create man-made structures in a nanometer size by drag the tip on the surface on a predetermined path. We call it lithography or AFM lithography. All right. Now the other imaging mode, AC mode. AC mode is very widely accepted, and you can most of the people actually can go over their entire career in AFM using just AC mode, or also known as tapping mode. As a matter of fact, 80-90% of the sample can be done just by AC mode or tapping mode. You can vary, if you know some of the contents that's being covered with the previous e-seminar. You can control the parameter to engage in attractive, repulsive, or high repulsive, or high force tapping, or whatever. And you can actually imaging the sample in very wide range of physical properties. The biggest advantage is, of course, there's no lateral disturbance, and therefore your tip no longer scratch your sample anymore. However, the problem with that is that you cannot clean the sample with this imaging mode. And then, of course, AC mode has its own list of advanced imaging mode. For example, here EFM KFM is AC mode, imaging mode, and the MFM, magnetic force microscopy, or other imaging modes, or AC mode based. Here's some examples of AC mode. Something soft, something easily can be disturbed by the tip, scratched by the tip, like polymers, proteins, soft samples, are ideal to imaging only with AC mode. Now, let's go over our next topic, choose of tip. Here is my impression of the market of the AFM tips. You go to buy a tip, and you're lost into the sea of AFM tips, or a wall of AFM tips, whatever you call it. So many different kinds. In this confusing list of cantilevers, I always wanted suggest people to look at the basics. Always go to the basics to understand what determines the difference between different AFM tips. Here's a drawing of AFM tip, and it has a chip, and it has a cantilever, and it's a tip. And then the things that tell the difference between tips are basically the cantilever shape, the tip sharpness, aspect ratio, and so on and so forth. Okay, let's go to look at the contact mode cantilevers. A contact mode cantilevers normally are having low spring constant. For example, it's about 0.5, 0.01, because when you image the sample, you don't want to scratch it. And therefore, a softness is very important. And a lot of tips, you can see that they'll have multiple tip designs, but you know, the benefits of the multiple tips in this case is allow you to give multiple choices, because making one tip and making 5 tips, the cost is the same. Now, AC mode tips. AC mode tips are mostly with high spring constant, because in air, when you image it, tip and sample has capillary attractions, and these attractions could cause the tip quickly lose its energy and stuck to the sample. Therefore, you need a stiff enough tip to maintain a constant, stable vibration. And a stiff cantilever, typically, when I say stiff, the spring constant is way above 1, typically 5 to 40, and the resonant frequency is from 60 to 300. Of course, you can also buy cantilevers with about 500 kilohertz or megahertz. Now, and you remember one thing is that when you do AFM AC mode imaging in liquid, you actually don't need to use quote-unquote AC mode or tapping mode tips. You can use contact mode tips. That's because in liquid, there's no capillary force, and therefore the tip does not stuck to the sample easily, and therefore you can use softer tips. So in liquid, you can just use tips that are any kind, and typically using contact mode tips to imaging in liquid. Now, by the look of it, how do you know I'm holding a AC mode or contact mode? The contact mode tips typically, because I just said before that it is typically very soft, and therefore if it is the single beam tip made of silicon, it is long and thin. And then typical silicon nitride tips are contact mode tips. So if you see something triangular, It's made of silicon nitride, and then therefore it is soft. An AC mode tip or tapping mode tip typically are very stiff, and then therefore it's a single board, diving board shape and very short. So that's a quick way to tell the difference between a contact mode and AC mode tip. All right, the next most important thing about choosing a cantilever is its sharpness. Sharpness actually can be described by two separate ways. And actually it means very different things. The first is what I call an aspect ratio. Basically, a very long tip could be not sharp or clear. There's two different part of the cantilever. The first part of it is the very end of the cantilever. Can I draw it here? And at the very end of it is described by this curvature, radius. So if you can equivalent this cantilever tip with a sphere, and the radius of sphere determining the sharpness of that very end of it. And therefore, this can be used to describe the sharpness of the tip. And that's the very end of the tip. The rest of the height of the tip from here to here is described by this parameter called aspect ratio. Basically, how narrow is the tip, the rest of the height. So these are two different sharpness. And these two different sharpness has two different meanings. So if you're using the tip to image something that is has some very small features, the end of the radius is very important, because then, as you can see here in this case, at this moment, the tip actually crashed a little bit, lose some of the sharpness at that moment, and the resolution of the image changed from the top part to the bottom part. And therefore, that is an example of that a sharp end of the tip is important to reach very high resolution, because you cannot achieve resolution that is sharper than the very end of the tip. It is your limitation of resolution. Now, the aspect ratio, animation here, the rest of the aspect ratio is important for you to image something that was a very deep trench. For example, in this grating has a very deep trench. And as you can see, the image of this grating is determined by the shape of the grating plus the shape of the tip. And therefore, it is important to have a very narrow tip. And therefore, in this type of sample, the aspect ratio is equally important. Now, let's take a look at special tips. And here is a normal tip, and here's a protruded tip. Here is the tip with a little crystal that has needle shape. And then also you can buy the tips that with a carbon nanotubes. All these tips has its own special place in improve your resolution and so on and so forth. Okay, in order to pick the right AFM tip for the job, and here are some rule of thumbs. I'm not going to read it from line to line. You can always download the PDF part, and then we're going to quickly move on to our next topic, is how to analyze your sample. So, analyze your sample. So when you, it's not every tip can, every tip is equal among the different samples. You have to look at the sample itself, and then when you look at a sample, you do a little bit basic analysis. For example, the physics property, how hard is the sample, how rough is it, the adhesion to the substrate, if the bacteria is attached to a substrate firmly or loosely. You can use a very different type of imaging mode. And some of the sample has static charge, and some sample has what we call depth-dependent complexity. It's kind of fancy word. That stands for some of the polymers. When you push it harder, the physics property differs when you push it into the sample itself. Feature size is also very important. You have to look at the overall size, height, width, and aspect ratio of a particular feature. Or some of the very small samples has very tiny features, and crystal steps has when you try to measure the crystal step, it's also important to know how high is the step before you actually determine what tip to choose, and then so on and so forth. So you have to when you was given a sample, don't just rush into pick a tip and image your sample. Ask the owner of the sample. Ask him to say was it on the surface? Is it bacteria? Is it cell? How big is the cell? If it is a molecule, how large is the molecule? Because a molecule could be very small and very large, and so on and so forth. So understand the size of the feature is also very important to determine the choose of the tip and choose the parameters like scan speed and so on and so forth. Next thing is to take a look at the surface chemistry of the sample. A sample with different kind of functional groups, if it is hydrophobic, hydrophilic, or it's inert or highly reactive, will also determine what kind of parameter and what kind of tip do you use. If you have a sample which is, for example, a silicon sample is very interesting because from my experience, when you try to using a stiff cantilever to image a silicon sample, you can easily dull your tip if a parameter is too strong. So take a look at the surface of it, because I believe it's the silicon tip has a high, it's very hard, and your samples are very hard, and tip and sample can bound during tapping, and then when the tip lifts from the sample, the tip could lose materials because of hardness and affinity between your sample and the tip. So take a look at the surface chemistry of your sample. What sort of adhesions, what sort of friction force, and so on and so forth. That can also help you to understand the interaction between tip and sample and help you to determine what kind of parameter it is. And also, of course, what sort of thing do you want to see? I mean, when we say that we do an AFM experiment, it's not just one experiment. It's a wide range of experiments. For example, are you interested to just look at the surface topography, measure the roughness, coverage, want to measure the size of the particle, or do you want to study the chemical property, physical property, or you wanted to see something that's happening in real time in situ? Or some people say, hey, can you measure a thickness of the sample? And how do we do that? So when someone gives you a sample, or sometimes you wanted to go to an AFM lab to run your own sample, always ask yourself, what is it you want to see? And therefore, they can also use that to determine what sort of parameter you use. Okay, that's the introduction part. It's a little too long. So let's proceed to the next one. Analyze interest advanced topic. In this presentation, we don't have time to cover these advanced topics, and I will give the list of these advanced topics, and we'll cover the next portion of this presentation. Maybe not today, maybe in a month or so. Okay, case studies. That's the purpose of today. Because it's we find it that even we discuss a lot about what sort of parameter you use, what sort of tip you use, what's the principle of that, and so on and so forth. People still ask me, what do you think you should use to my particular tip? So I come up with this list of, I come up with this form. I call it AFM matrix form. And right now the form has maybe 10, 20 entries. And hopefully through time we can have more entries. And I'm going to have this form available. If you email me, I will pass the latest form, and maybe I can periodically post the form in some social media, and then you can download it. And I try to make the suggestions of what tip to use, what imaging mode to use, using this form. So this form contains several parts of it. Let me expand a little bit. First of all, the first part of the form, from this row to this row, are the analyze of your sample. The sample name, the shape of the sample, the imaging media. Are you imaging water, in air, ethanol? What are you interested in? What do you want to see? Do you want to measure step height, topography, and then the expected feature size in X, Y, and in Z? The second part of the form contains the information about imaging mode and parameter suggestions. As you can see, this is the beginning of construction of this form. And I could not list everything. This is everything I can thought about in the last week. Here, content represents content. contact mode, force modulation, conductive AFM, and so on and so forth. Here, these are the parameters which tip you use. You want to use a sharp tip like 5 nanometers, or you want to use a dull tip like 50 nanometers. And 5 to 50, I mean, this is a range. Let's see. This is a range of parameters. Basically, it'll work from 0.01 to 5 of spin constant. However, I believe 0.5 is ideal. So you have a range and you have a slash an ideal optimized value. So this allows you to basically make a choice and even allow you to deviate from that choice because, let's say, my experience only covers some part of it and not everything. And hopefully this will act as a suggestions. I cannot say that I know everything, and maybe someone here can make a suggestion for me and say, hey, I use this tip and it works better than your parameter. If that's the case, please tell me. Again, I'm going to post my email here, and one second, I'm typing, and then that any suggestion be highly appreciated. Okay, let's go into the real case study. And here is the first sample. And again, this is the format I'm going to use for this presentation and next presentation. The top of it is going to be made of different kind of samples. In this case, is a gold 111 surface. That's a sample. And then sample geometry, you can use thin film, you can use bead, imaging media, and what things they're interested. Are you measuring step height, or are you look at the topography? And the size of feature in the XY is 50 to 200 nanometers. That's the size of these patches of terrains. And height is 3.5 angstroms. That's actually 3.4 or something in Z. And here is our two suggested imaging modes. Here, contact mode is ideal. And then you can use a cantilever that is not very sharp. 10 nanometers good enough. The reason is that if you want to measure the step height, you actually don't need the very sharp tip. And because it's a contact mode, a sharp tip actually gets blunted very quickly anyways. The spin constant ideally is 0.5, 0.01 to 5, it all work. And force is 1 nanonewton. This is a little bit in the high side in low force. That's because at this force, as you can see, this image is very clean. That's because your tip is actually cleaning away the junks and contaminations. We all know that gold is very easily to be contaminated. So use a little bit higher force in contact mode can clean your sample. And here is the scan range. 300 nanometer gives you a very beautiful view of one terrain. And you can scan from 150 nanometer all the way to 10 micron. Actually, in 10 micron, you can still resolve atomic steps. LFM, frictional force, is also very good. There's a little typo here. We should put 150 here, not 500. And everything else is the same. Okay. Next example, case study. Next is atomic lattice of crystal samples. For example, gold, 111, mica, and graphite. Here again, use a slightly blunted tip, not very sharp. This because when you're imaging crystal lattice, you actually the result is not individual atoms. The result is a lattice, and therefore it's some sort of average across the area. And then it depends on a relatively strong interaction between tip and sample. And there's many reasons, but I find that the slightly not so sharp tip actually works quite well. Spin constant is the same as imaging these crystals in liquid. 0.5 is relatively stiff in the contact mode area, and then 1 as a force, also in the low force, is relatively high, 1 nanonewtons. Scan speed, you can scan relatively fast, about 10 lines per second, even 20, that you can resolve this very well. And then sometimes we find that the LFM, or frictional force imaging, works quite well when you try to resolve the crystal lattice of certain samples. Okay, next case, atomic steps of silicon. In this case, silicon, of course, you can, for example, silicon carbide and all these atomic crystals are very similar to each other. They are relatively stiff and relatively hydrophilic, And ideally, you actually image them in ethanol or isopropanol. Air will also work. This is a polysilicon wafer, actually. Sample is typically flat, and then your imaging interest is measured in step height and topography. Feature size in XY is 100 nanometer, and Z is at 0.3 nanometers. Now, here, I believe contact mode is still an ideal imaging mode because of its capability of cleaning the sample, because the sample is hydrophilic, and a hydrophilic sample can attract contamination very easily. And therefore, contact mode with a strong force. For example, here I suggest the force is 1 nanonewton, relatively high, can clean the sample very well. AC mode can imaging this too, but with the exact same sample, AC mode imaging appeared to be relatively dirty. That's because AC mode, as I say, it does not clean the sample as contact mode as well. So ideally, using a relatively dull tip, because as I say, when you're imaging step height, it doesn't matter about the width of the height, and a dull tip works as well as a sharp tip. And then a spin constant, also 0.5 is ideal. From 0.01 to 5, it will work. And force about 1 nanonewton, scan speed 2 hertz. From 0.5 to 20 hertz will work. And scan size, about 2 microns, give you a very ideal, beautiful image. In this case, image 3 microns, very similar to it. Okay, let's go to the next example. Porous alumina. Now, take a look at this sample. Porous alumina, this alumina is very hard, it has very high hardness. And it also has a vertical features that is equal to the lateral feature. In this case, the feature size is 100 nanometer in XY and 100 nanometer in Z. It's deep, and therefore it fit a profile of imaging something that's very deep and sharp. And you can image them in air mostly. In liquid, it does not make any difference. So I would suggest imaging this in air. This porous alumina, here's the suggested 2 imaging mode, contact mode and AC mode. When you use contact mode, tip radius 5 is good enough. That's because when you use a sharp tip in contact mode imaging in air, the tip, a 2 nanometer sharp tip, can be blunted into 5 nanometer without you even knowing it. Contact mode can easily dull your tip. Spin constant, I would choose a very soft tip. That's because, as I said, we don't want the force to be too high. And force will be small, lower than 1 nanonewton in scan speed and scan range, so on and so forth. A 500 nanometer scan gives you a very nice, beautiful image. Of course, you can scan 150, everything appeared to be very big, and 10 micron, and everything appeared to be very small. But 500 gives you ideal imaging quality. AC mode actually give you a very good result. And here, AC mode, I would suggest a very sharp tip, in this case, 2 nanometers. 2 nanometer tips in a lot of tip manufacture, they call it ultra sharpened or ultra SSS and NCH. In the case of nano-sensors, it's called the super sharpened silicon, SSS, and that's 2 nanometers. A 2 nanometer tip for this kind of sharp feature can resolve this feature very, very nicely. And spin constant of this tip, you can use it from 5 all the way to 100, and then the tip I use the most is 40 newton per meter, 40. And these 40 newton per meters are typically at 300 kilohertz in resonant frequency, because you can use from 60 all the way to 350. And this tip gives me a very ideal result. And force is you can use from attractive all the way to repulsive strong force, but a small repulsive force gives you a very ideal result. That's the reason is that when your repulsive force is too high, again you can blunt your tip from 2 nanometer to 5 to 10 without you even knowing it. So a small repulsive force is ideal. Scan speed slowly, because the sample has a very sharp vertical features. Using slower scan speed can help you to get the best resolution. And scan range 500, same thing. All right. The next case, let's see, nanoparticles. Here, let's see. Okay, nanoparticles. When I say nanoparticles, it typically ranges from 1 nanometer to 50 nanometers here. A lot of times people give me a nanoparticle sample, and then I'll ask them what's the size of your particle. And they say, oh yeah, maybe 0.5 micron or 100, 200, 300 nanometers. I'm going to not call these quote-unquote nanoparticles nanoparticle. I'm going to call it micron and submicron particles, because the technique and tip choice between a nanoparticle and submicron particle are slightly different, and the tip requirement is also slightly different. So here, nanoparticle, I will call this 1 to 50 nanometer nanoparticles. Anything bigger than that is not covered by this particular slide. It'll cover by a slide later on. Here, the nanoparticles, I would suggest only image with AC mode. Contact mode does not even work. And image it with a very sharp tip. Again, 2 nanometer tip, 40 newton per meter, and 300 kilohertz is ideal. Force, you can use a relatively big repulsive force. I would assume these particles are not easily to be crushed or deformed by vertical force, and therefore strong force is good. The scan speed low is also good, because you don't want to kick those particles around by too much lateral interactions. And scan range, 1 micron is ideal. In this case, I think it's about 1 micron. This is an image of 5 nanometer nanoparticle. 1 by 1 micron gives you an ideal ratio of features versus blanks. All right. I also list a bunch of imaging modes like EFM, KFMs. Now, EFM, KFM can be used to detect electrical property. For example, if a lot of people say, hey, I want these particles are made of silver or gold, I wanted to using conductive AFM to study its conductivity. All right. What's wrong with using conductive AFM to study conductivity? And here, as you can see here, the CSAFM is not listed and contact is not listed. The reason is CSAFM is actually a contact mode. And contact mode does not work with nanoparticle very well, because when you use contact mode, the tip will sweep away those nanoparticles, and therefore you cannot use contact mode, and therefore you cannot use conductive AFM. So you cannot use conductive AFM to study the conductivity of a nanoparticle. That's the first reason. The second reason, for example, in this case, the gold nanoparticle is on the surface of mica. Mica is an insulator, and therefore you cannot ground the sample, or you cannot form a closed circuitry, and therefore conductive AFM does not work. So you have to use EFM and KFM. And in KFM imaging mode, there's one imaging channel. It's called DC-DC, or capacitance gradients, and then experiences that when you have a high conductive particle, the high conductive particle, even if it's surrounded by non-conductive insulators, it still generates high capacitance, and therefore you can see a strong contrast in capacitance gradients image. In this case, these particles are embedded in rubber, and then using capacitance derivative from KFM, you can see the conductive particles, and you can say, oh, these particles are conductive, even if it's not grounded. And some people also do the lithography with this particle. In this case, lithography means that you're pushing these particles with AFM tip, and then using this push it around particle to form a little letter of the logos and so on and so forth. And this is a list of suggested cantilever to do lithography. 5 Newton per meter tip, and relatively dull tip. You don't need a sharp tip. Relatively dull tip is fine. And so on. Okay. Here's the end of this example. Let's go to the next case study. Biomembranes. In this case, it's a liquid bilayer. A liquid bilayer, typically you image them in water. You cannot image in the air, because the lipid bilayer, when it's exposed to air, it collapses and then roll around, form a little sphere like liposomes. So you have to image them in water. And when it's imaging water, you can actually image quite well with contact mode as long as you use a very small spring constant tip, as long as you're using actually a dull tip. I don't suggest use a sharp tip. The reason is simple. A sharp tip, the tip can penetrate it with a little bit of force. So you need to use a dull tip. And then force constant as small as possible. Actually works from a wide range. Scan speed is normal, size is normal. AC mode can equally work well. Again, I suggest using the dull tip. And because AC mode in liquid, you can use a relatively low spring constant tip. One works well in AC mode. Actually, AC mode, I list both AC mode and MAC mode. And then scan speed and force, again, using 0.1. 0.1 is a very small scan speed, scan force. So, imaging those membranes, use a soft tip and a small force. You can also do force pulling and indentation using this sample, and these are the suggested cantilevers. Force pulling, you use a very soft tip, and indentation, use relatively high force tip. That's because a very soft tip probably cannot easily penetrate those membranes. Okay, next example, block copolymer. A block copolymer is a soft sample, and it has a very fine features, about 100 nanometers. I think sometimes it's even smaller, 50 nanometers maybe. And then the feature size on Z is very small. Up and down is very small. Typically, people are interested in studying the morphology and hardness, and you can most time imaging them in air. Block copolymer. You can study it with AC mode or force modulation. And here's the tip and parameters suggestion force modulation. You use a tip which is 5 Newton per meter. This is called FM tip. If you want to buy an FM tip, it says FM. The box will print from 1 to 10. It's typically 5 Newton per meter. This is the resonant frequency using a variable force. Scan speed, you can get a very good result. AC mode, typically using a kind of like regular sharpened tip, 5 Newton per meter. These cantilever tips are typically called regular sharpened, not super sharpened. And anything sharper than that is a waste because you cannot resolve anything better than 5 nanometers. Anything more blunt than that, you cannot resolve those features nicely. So 5 is good. Spring constant, 40 Newton per meter is ideal because you actually do need to apply a little bit of more force into the sample to get a good contrast. 150 kilohertz and 300 kilohertz, they equally work very well with this kind of sample. Force need to be relatively high, 1 to 5. Scan speed and scan size and so on and so forth. You can also do lithography, and doing lithography in a polymer sample, you need to have a relatively sharp and relatively, you don't need the sharp tip. You crash your tip anyways. And you need to have a relatively strong tip, 5 Newton per meter to 40. They can both cut features into a polymer sample, and so on and so forth. So let's go to here you can also do indentation using a relatively strong tip to measure the modulus, hardness, and so on and so forth. And then tip radius need to be dull. You cannot use a very sharp tip to indentation to expect to have a good, reliable result. Typically, when you do indentation, you use a relatively dull tip. Here's a contact mode. That's the reason I do not suggest with contact mode, because as you can scan, you can scan with a contact mode, and as you scan, you actually gradually destroy wear your sample down. The sample is changed. Here is an interesting example of this block copolymer image with AFM AC mode. When you use a very light tapping, in this case a tracking mode, it looks like this. As you increase your force, gradually the topography transforms itself into something that looks very different. And that's exactly the reason why I list a wide range of parameters. That's because as you change the parameters, your actual image changes, and then the reason is simple. As you can see, this last image is a zoom out image of the exact same sample with a small imaging force. As you can see, the center square was actually not permanently, it's been changed after you image it with a strong force. You actually pushed the very top layer sample and compact it, and then this compact sample, before it's relaxed back, it's actually been changed. So, as you can see, that's why I list a wide range of force when imaging rock copolymer. And if you want to look at the Lamana structure, you need to use high force. Okay, next example. DVD engravings. These samples typically are made of very stiff material, silicon or hard plastic or metal, and they typically have a sharp trench. So both contact mode and AC mode will work. For hard samples, contact mode can equally work very well. Contact mode uses a very sharp tip is pointless. That's because your tip is crashed anyways. The first 2 nanometer can become 5 when you approach. Spring constant works with a wide range, and force need to be lower than 1 nanonewton. High force will blunt your tip. Scan speed and scan range. Here I do not put a number here, as I would say pitch times 50 to 20. If the pitch, the distance between this line and this line, is 1 micron, you need to scan 5 to 20 micron to get a very nice image. Pitch is the periodicity, the distance between this line and this line. AC mode. AC mode, I would suggest using a 15-degree cantilevers. This is what people call ultra-sharpened with high aspect ratios. This is important because if you have a tip that has a lower aspect ratio, it does not reach the bottom of this trench of the gratings. And force is relatively high force, and scan speed median. And then again, scan range is pitch times 5 to 20. Here is a close look of different tips of ultra-sharpened. When you go shop for a sharpened tip, the sharpened tip could mean different things. In this case, it's a growth of a needle-like crystal and make the tip very sharp. This is useless for this type of sample. That's because this tips only has 100 nanometer height, and these trenches are several hundred nanometer deep. And this kind of sharp tip at the very end is also not very useful. That's because the sharpness only lasts the first 20 to 50 nanometers. What you need is a spike tip that has a very high aspect ratio throughout the first hundreds of nanometers. That's useful for imaging this type of sample. All right, next example. Calcite. Here the interest is to study the step height and also do in situ observation of dissolving a calcite in water. And I would say contact mode is ideal. That's because the sample is very hard. And you don't need to have a very sharp tip. A sharp tip does not give you any more information than a blunt tip. A relatively mediocre tip is good. Spring constant of the tip can work from 0.01 all the way to 5. I probably should suggest something like close to 0.01. And force need to be relatively not too high but not too weak, because that as you scan it, you want to scan it fast. In this case, 5 hertz, and you want to tip the sample to firmly attach to each other. When you use very small force, tip can flow off the sample when there's a drift. AC mode can also work, but I put a little thing blue here, and that's because AC mode goes a little bit slow, and it actually does not remove any contaminations. It does not give you any advantages, so I put a little blue color here. Okay, next example. Living cells. A living cell, I would suggest using contact mode with a very blunt tip, because a cell is large. The cell typically is several microns to 10-20 microns, and using a 5 nanometer tip and 20 nanometer tip does not make any difference in this large scan size. Spring constant need to be as small as possible. Force need to be near zero. Scan speed, mediocre is fine. AC mode, you can use Mac mode or AAC. Again, sharp tip is pointless. And you need to use a very soft tips. And force is near zero. Scan speed need to be lower, and so on and so forth. Now, when you try to measure the stiffness, here is the parameter for doing indentations. Indentation, you need to use a dowel tip and then spring constant 0.121. When you use a very soft tip, the tip does not push into the sample very well, and therefore your data may not be very reliable. And you can also do force pulling, again 0.1 to 0.5 Newton per meter tip, not too stiff, not too soft. Now, fixed cells. Fixed cell is very different from a living cell. A fixed cell typically are much more stiff than a living cell, and you can reach much higher resolution, but you need to use AC mode. Here, I put AC mode as red and contact mode as blue. Contact mode can work well, but it was near zero force. However, AC mode was a relatively strong force, can resolve much more details when you use AC mode. AC include Mac mode or AAC. I believe Mac mode works better. And tip radius 5 Newton per meter, because you can actually achieve quite good resolution. A sharper tip 5 is good. 2 nanometers is completely not necessary because these soft samples when you use very sharp tip, and then when you scan large area, it doesn't make a lot of difference between 2 and 5. So 5 is good. Spring constant, you can have a wide range of spring constant. Force is relatively high in the low force, in the repulsive region. Speed and scan size from 0.5 micron to 5 micron. Actually, we can actually do 50 microns. I should put another zero here. If your cell is very large, and 2 to 3 micron is ideal to resolve the little bit details on the surface membrane of a fixed cell. So as you can see, a fixed cell and a living cell I suggest use different parameters and tips. Collagen fiber. Collagen fiber are large fiber-like proteins with very interesting structures, and I believe only AC mode works because collagen can stick to a contact mode tips and allow the tip to tear the sample and therefore result in bad imaging. And then relatively sharp tip. 40 Newton per meter, 150 kilohertz to 300 kilohertz, and using relatively high force, you can resolve a lot of details of these type of samples. You can also do indentation to measure the stiffness of the sample and using 1 to 5 Newton per meter tip. When you do indentation, a sharp tip does not make sense. A relatively blunt tip is good. Okay, next example. DLC film, diamond-like carbon. This kind of sample are very stiff because it's diamond, and therefore contact mode and AC mode works equally well. And then these are suggested tip radius 5, using a relatively high 2.5 cantilever. You can scan real fast. Force need to be low because high force can wear down your tip very quickly. When you do AC mode, also very similar to contact mode, but you use a 15 Newton per meter tip, and relatively strong force in a weak. It's +1. It's a relatively medium repulsive force, scan speed and scan size, and so forth. It's a relatively simple sample, and normally people only care about topography and roughness. Imaging in air and feature size of 10 nanometer in XY and 10 nanometer in Z. Next sample, DNA on mica in air. I would suggest you only use AC mode, and with a very sharp tip, 40 Newton per meter spring constant, 150 or 300 kilohertz. The force need to be kind of not too high, relatively low, because you can compress your sample easily if you use high force. When you use the force is too low, it's also kind of difficult to track the surface. When you use the force very high, DNA can appear to be very flat. scan speed need to be slow. This is a very similar sample, protein fiber in air. Everything is actually very much the same compared to DNA imaging in air. Now, DNA in water, I would suggest to use MAC mode or AAC mode with a sharp radius. That's because in liquid, you can actually achieve very high resolution when you use a very small force. And in this case, this is DNA, and these are actually individual protein molecules. And then this is the parameter when you do force pulling. Another sample, which is protein imaging in liquid, is very similar to DNA imaging in liquid. And actually, all the parameters are very much the same. They have very similar characteristics. Okay, the next case, is what called a micron or submicron particles. In this case, they're 100 nanometer size. People call it nanoparticle. I'll call it submicron particles, because it requires very similar characteristics of tip and parameters compared to, let's say, in this case, half a micron particle. The imaging was AAC mode in air with a mediocre sharpness tip, 40 newton per meter, 150 to 300 kilohertz, and use a relatively high force. High force makes the imaging scan resolution very good, and scan size 2.5 micron, several micron is ideal. You can also do indentation with it with a relatively dull tip and relatively medium stiff cantilever. You can actually crush these particles and measure the modulus and hardness. Okay, this is the last example, self-stand monolayer of trial. And this type of sample, I would suggest mostly doing contact mode with you can actually use a very sharp tip, because in contact mode, you can control the force to be very small, in this case, 0.01, with a soft tip, and then you can achieve very high resolution. You can also use this kind of sample to do lithography. You can cut a little symbol of yours using a very sharp tip, actually, and sharp and relatively in soft tips, slightly more stiff kind of cantilevers, and you can cut something that's very nice. Now, I try to cover my past 15 years of experience with this presentation, but I had to leave all these topics out. There's a longer list as for last hour. And these topics I will try to cover in our next part of it, and a lot of these things are very advanced topics. For example, combine AFM with surface plasma resonance, what could be used. And then this needs to be continued in our next presentation. And thank you, everybody, for your time. I would like to take some questions.
Thank you so much, Dr. Xu, for a very informative presentation. Ladies and gentlemen, we have opened a poll on the lower right side of your console. We welcome your feedback on our presentations, and thank you for taking the time to answer this survey. As always, your participation is optional and may be recorded. Now to the question and answer portion of the presentation. You may ask questions at any time by putting them in the question box. We will answer them in order. To ask questions over the phone line, press *1 on your touch-tone phone, and the operator will open your line. If your question has already been answered, or if you wish to remove yourself from the queue, press the *2 key. So let's look at the questions. Looks like we have quite a few. The first question.
Do you want me to read the question? I'm sorry, Bernard. Do you want me to repeat the question and answer it myself?
I can go ahead and read it, unless you would prefer to do that, Dr. Xu.
That's fine. Please read it.
Okay. In the case of imaging the grating with very high aspect ratio tips, how do you handle the lateral attractive forces between the tip and sample?
That is a very interesting question. I do have lots of problems with lateral attractive force. In this case, for example, this particular sample, I actually waste one tip every sample. That's because the lateral attractive force between the sidewall of the tip and the sidewall of the things cause the amplitude to drop a lot, and therefore you actually have to reduce your set point a lot in order for the tip to reach the bottom of it. But when you do that, you also blunt your tip. Someone gave me 10 of these samples, and I actually wasted 10 tips. Every time at the end of imaging, you do reach the bottom of the gratings, but also you completely blunt your tip, and this tip is useless for the next sample. So actually, this is a difficult question for me. Now, what I suggest, these attractions, I believe they're static charge attractions, some sort of electrical attractions. I did not try it, but I think that will work. Is that you can actually image these gratings by immersing them in water, and then imaging it in water, because when it's in liquid, those kind of attractive force just disappears, and then you can use AC mode with a sharp tip. That's my way to deal with static force, very strong static force. I haven't tried it, so I would say this is at this point as a suggestion. If someone happened to have this sample, we should have a chat, and maybe I can try this theory, this suggestion a little bit. This way, maybe this one sharp tip can last more than one sample. And actually, this is a very interesting question, because I was faced with the exact same problem.
Next question. What type of probes can we use for high-resolution imaging? Cell pores, DNA scanning, and in what mode should we scan? Contact, AC mode?
Well, this is not one question. This is a couple of questions. DNA and the cell; these are two very different type of things. DNA is when you try to get the best resolution, you put the DNA in a very flat sample, and that's because, as I said before, if you want to observe 1 grain of sand, you put this 1 grain of sand on the surface of a piece of glass, because you want to observe something small. Your substrate will be flat. So use a flat substrate and using very sharp tip, you can achieve high resolution. Now, cell pore is completely different. Let me move to a cell, number 38. A cell has a very high roughness. I mean, in this case, the Z of this cell feature is hundreds of nanometers. How do you observe something that is 10 nanometer in a 500 nanometer feature? It's the most difficult thing. And I would say I'm not an expert on that. The best way is probably fix your membrane on a flat substrate and try to do it that way. And using MAC mode, I would say. But again, I need to cover it maybe next time. I actually don't have material this time. That's a different way to say it. I don't know. I'm not sure.
Next question. Hello, I use contact tip mode for analyzing electroless nickel-plated substrates, which has small grain boundary-like structures. At times, the scans don't show any pattern. How can I increase the sensitivity of the images?
Analyzing electroless nickel-plated substrate. That's probably very similar to I haven't covered this time. Very similar to electrochemical plating sample, which is a large electrode with a tiny little crystal on the surface. I would say using a medium step tip, like 0.5 newton per meter, medium to soft, 0.5 to 0.1. And then control it, and image in liquid is very important, because contact mode imaging in air, actually your resolution is not very good, because the capillary force, your forces are very high. Directly imaging them in liquid with a small force, that would be ideal. And I cannot talk about anything else. Just imaging in liquid with a small, with a soft to medium tip, that would be ideal.
Thank you. Green boundary-like defects are difficult to identify with rough surface scans. The roughness of the surface is roughly 20 angstrom. So what are the key parameters in leveling the image?
So I don't know exactly what is the sample. We could check later, but here, let me make a guess. Just a grain boundary, like defects, and these defects is actually mixed up with other roughness of the sample. So the grain boundary is some sort of defect, or some sort of roughness. Your sample is also some sort of roughness. So here's the difficulty: is that how do you tell the difference between one roughness and the next roughness? By just look at the physical shape, you probably cannot tell the difference. What I suggest, how to differentiate two different type of roughness, is to take a look at its other physics property. For example, stiffness. For example, adhesion. For example, electrical property. For example, if there's silicon boundaries and then grains, the boundary and grain, they might have different kind of electrical property, capacitance, and so on and so forth. And therefore, maybe you should think about imaging mode that can differentiate this type of differences in physics property, instead of only rely on the roughness itself, because roughness does not tell the difference.
When will you present a talk about AFM on batteries?
Next time. I actually had a presentation of AFM on batteries. I believe, let me type the website that you can actually download the previous talk. It's agilent.com/CHEM/ESEMINARS. I believe that is the one. Yeah. It's agilent/chem/eseminars. I actually had one of these AFM on battery study, and then there's more work than just choose the tips. You have to modify the chemical cell, the EC cell, so that you can, because when you do, I mean, battery, I will assume, or those lithium battery you talk about. If you talk about the regular batteries, it's easy. You just construct the AFM electrochemical cell. When you do lithium battery, you have to construct all these things inside a glove box, and the protection of atmosphere, that there's no oxygen and humidity, and therefore you have to construct the whole electrochemical cell with your gloves on. And that's very difficult. And I could talk about how to modify your electrochemical cell, so you can actually put all these things together with two tweezers. And if you're really interested, again, email me, and then we could talk on the phone, and I can show you the work I have done with the battery work. And it's actually worth an entire hour of presentation. I probably cannot cover it in this today. Let's talk later.
Next question, and you may need to read this yourself, Song, but I'll give it an attempt. Hi, Song. In slide 34, you showed images with different forces, and it showed best image at 5 NN. I'm not sure whether that's
Newton per meter, non-Newton, yes. Yeah.
Okay. What is this force actually? Is it a set point value? Where do we apply this force?
This is also covered with one of the early presentations named The Physics of AFM, part number 3, I believe, probably part number 2. We can also chat that. You can actually measure or calculate the repulsive force between tip and sample, and you can actually manipulate it by control the drive and set point. And how to do that, that's covered by that presentation. And this is the 5 nanewton is actually a very high force, and the way to do that is increase your drive. How high it is, it's relative. If you really want to measure the force, you can actually measure the force by tapping one cantilever on another cantilever and measure the bending of another cantilever. That can be easily done because you can mount a contact mode cantilever with known spring constant, and then approach your AC mode cantilever on that contact mode cantilever on the back side, and then as you fix your drive and the set point, you can do amplitude versus distance curve and analyze that curve. We could get the actual force when you use different drive and set point. I've done that once, but haven't put together a presentation yet. If you really want to know it, we could cover it in a future topic. Now, by estimate, if you use a 40 Newton per meter cantilever, if your drive is very high, so high that you actually run out of your signal range, you could reach the force as high as 5 nanewtons. So 5 nanewton of force is actually the upper limit of a 14 newton per meter cantilever. But that's just an estimate. I haven't actually measured in this particular case. The way to control it is increase your drive.
The next question. For capacitance measurement of nanoparticles using AFM, what is the principle? I am curious how it works.
That's slide number 31. Again, this is also covered in one of the early presentations. It's called a Beyond Tapping mode. You can, again, find it on that eSeminar download. And again, we could talk about it if you email me. And the way the principle is that when you have a conductive material on the sample, even if it's surrounded by insulators, when you apply a voltage to your tip, the voltage on the tip can actually induce a dipole moment on the conductive particle. So this tip and this induced dipole moment will have attractive force. And then if you not just simply apply a voltage to the tip, you apply an AC voltage to the tip. This AC voltage can cause this dipole moment to flip around at the same frequency of the AC voltage, and this can induce a attractive force between the tip and sample at double the frequency of the driving bias. This double frequency vibration is the indicator of capacitance between tip and sample. So again, this is a very short answer, and then if you want to know the details, that presentation is called Beyond Tapping mode or Advanced Imaging mode based on tapping, and I talked in detail about this, the principle of that. Again, go ahead, go to that website. You can download that previous talk. If you want the original PPT, email me. I'll send to you.
I wanted to let the audience know that you did put the URL for the previous seminars in the chat box.
In the chat box, yes. Yeah.
Yes. Dr. Hsu, do you have any questions in your personal chat?
Personal chat? Which question is that?
I say, is there a question there? I can't see the box, the chat
that
you have.
Yeah, let me take a look at that. Personal chat, my Q&A, growing boundaries. Let me read one by one. If I have really hot samples, that's recovered. I know vesicles. Oh, okay. Here's a question from Vasily Chernyshev. The question is: we work with nano vesicles smaller than 100 nanometer. We would like to absorb them on mica and image with AFM in liquid. What tip would be the best for this type of sample? This type of sample is very similar to, let's see, which slide is this? I don't remember. Oh, yeah, this is it. Here it is. I would say use a relatively blunt tip, and if you want to use AC mode, I would say medium to stiff, 1 newton per meter, 0.1 I think is quite well. Contact mode, even very soft contact mode, people work. AC mode, 1 newton per meter. I'm going to say 0.5 is also going to work. And just make sure your tip is not very sharp, and then you can get that quite well. The next question is also from Vasily, and what parameter should we use? The parameter you should use is very similar to imaging in AC mode using a soft tip in liquid, using relatively small force. That's the key, a blunt tip with small force, because it's try to avoid a tip to penetrate your sample. The next question is from Gisa Starovengadan. The question is, where can we find the earlier presentation? Oh, the earlier presentation is, you can find it in either the presentation before the 2012 is found it in, let me type in here, afmuniversity.org, and later one can be found on the agilent.com/chem/eseminars. If you wanted it, you could email me, then I can also post them or email to you myself.
Thank you, Dr. Hsu. Nikki, is there anyone holding on the phone line?
There are no questions on the phones.
Thank you so much. At this point, it appears that there are no further questions and we are out of time. So please join me in thanking Dr. Song Shu for his presentation. On behalf of the Electronic Measurement Group at Agilent Technologies, we thank you for joining us today, and we hope to see you at a future e-seminar. We will leave the question box open for a few more minutes to receive any feedback or additional questions, but we are now going to close the audio lines. Thank you once again for attending from Agilent Technologies. We wish you good day.